Today we're going to be talking about systems of equations, and we're going to be solving systems using the graphing method. Let me see if I can write on here, using the graphing method. So first let's talk about what a system of equations is. In this first example, your family is taking a vacation, and two vehicles are used to make the trip. The first vehicle leaves at 4:00 p.m. and sets the cruise control at 50 miles per hour. That's a rate. 50 miles per hour, which means that's the number that's going to go in front of our variable. The second vehicle leaves 2 hours after the first vehicle and sets the cruise control at 75 miles per hour. There's another rate. After how many hours will the second vehicle catch up to the first vehicle? After how many hours? Okay, we're looking for time. So let's write some equations that represent these two scenarios, or these two cars. We're going to let f of x equal 50 times x. Remember that 50 miles per hour, that's our rate. We're going to put that in front of our variable, which means our variable x is going to represent time, or hours. So when I graph it on my x-axis, what am I going to label the values on my x-axis? Time, or number of hours. So f of x, remember that's just a function's name. We're calling this first function f of x, and it's just our fancy schmancy way of writing this equation. So we're going to let f of x represent the equation for the first vehicle. And I've kind of got it color-coded here, right? So f of x is the line in pink, and I've got it labeled over here. Then we're going to let g of x equal 75 times x minus 2. And I wrote it like that because the second vehicle is going to leave 2 hours after the first vehicle. So what I'm going to do is I'm going to take my x value and I'm going to subtract 2 first because we're leaving 2 hours after that first vehicle. I put that inside the parentheses, but then that rate still goes in front of the x value. And if you want to, you can always rewrite this in slope-intercept form, which would look like this. 75x minus 150. Right? So really, I'm down like 150 miles when I'm starting. So we're going to graph both situations or equations on the same coordinate plane because we're dealing with two cars, two equations. So let's look at them on the same coordinate plane. So when I'm graphing this first one, f of x, that's the one in pink, g of x, that's the one in blue. Now notice this graph is just restricted to quadrant 1, right? This is just quadrant 1. And why do you think that is? Why do you think I don't care about what's going on all over here? Because time, we're not looking at negative time over this way, and I don't care about negative miles, okay? So really though, my y-intercept is at negative 150, which would be down here somewhere, okay? It would be on that line, but I don't really care about that right there. I just care about my starting point at 0 miles, which is on my y-axis. I'm starting 2 hours later, so I'm right there, right? And this first car has already driven that many miles whenever I've started, okay? Or the second car started. I don't know what I'm talking about. I'm driving. Or I guess it is your family. Okay. So what is the point at which the two lines intersect? Well, I've got that here for you. They intersect right here, that little dot right there, and it's 6/300. That's the point at which these lines intersect. Well, that point of intersection represents something. What does it represent? Well, we know our ordered pair is x comma y. Well, when you're talking about a word problem, everything means something, right? Our variables mean something. In this case, the x values represent time in hours, and the y values represent miles, or miles driven. So this point at 6/300, what does it represent? It represents the point at which they meet, the time at which they meet, and how many miles have been driven by both of them at that point. So the second vehicle, this is what it means. It means the second vehicle will catch up to the first vehicle, after 6 hours. So that's our time. Remember that question up there? After how many hours will the second vehicle catch up to the first vehicle? After 6 hours. But let's talk about what this entire ordered pair means. It means the second vehicle will catch up to the first vehicle after 6 hours at 300 miles driven. That's what that means. And that is a system of equations. A system of equations is a set of two or more equations containing two or more variables. Notice, we're graphing these on a coordinate plane because we have two variables. We have an x variable and a y variable. And we have two equations. We had f of x and g of x. That's a system of equations. It's just multiple equations. The solution to a system is an ordered pair that satisfies each equation. If it's a solution, it makes both equations true. So here's what it does. We just looked at it graphically, but what if I just give you an ordered pair and I give you two equations that look like this? How do you tell if this is a solution to this system of equations? Keep in mind, an ordered pair is written x, comma, y. What I'm going to do is I'm going to substitute each value in for its corresponding variable in both equations. And I'm looking to see if it makes both equations true. So let's talk about what that means. So in this first equation, 2x plus 4y equals 6. What I'm going to do is I'm going to replace x with 3 and y with 0. And I'm going to ask myself, or just simplify it and determine if it's a true statement at the end. So 2 times, remember I'm replacing, so I replace it with parentheses, substitute it with what I'm replacing it with, plus 4 times what? 4 times 0 equals 6. So my question is, does this equal 6? Well, 2 times 3 is 6, plus 4 times 0 is 0. Does 6 equal 6? It sure does. Let's go to the next one, and I'm going to change colors here. So it does satisfy that equation, but remember, for it to be a solution to a system, it has to satisfy both equations. So I have my y variable here. I'm going to replace 0 with y, and I'm going to replace x with 3. So instead of y equals 2x minus 6, I'm going to write 0 equals 2 times x, which is 3, minus 6. 0 equals 2 times 3 is 6. 6 minus 6 is 0. And that's a true statement. So it satisfies both of those equations, which means, yes, this is a solution to this system. Algebraically, we were able to substitute each x value and y value into both equations and determine that. Let's look at number 2. So number 2, and I'm going to change colors here. So in this first equation, I've got my x variable here and my y variable here, and I'm going to replace my x variables with 4 and my y variables with 1. So instead of 3 times x, I'm going to write 3 times 4 minus 4 times 1 equals 8. So my question is, does this equal 8? Do I end up with a true statement? 3 times 4 is 12, minus 4 times 1 is 4, equals 8. Then 12 minus 4 is 8, and I can conclude that 8 does equal 8. So it is a solution in this equation. But remember, for it to be a solution to the system, it has to satisfy both equations. So let's look at our next equation. I'm going to replace 1 for that, or I'm going to replace y with 1, and I'm going to replace x with 4. So instead of y equals negative 3x minus 6, I'm going to write 1 equals negative 3 times 4 minus 6. So 1 equals negative 3 times 4 is negative 12. 1 equals negative 12 minus 6 is negative 18. Does 1 equal negative 18? No, it doesn't. It does not satisfy that equation Therefore, this ordered pair is not the solution to this system of linear inequalities. Meaning, this point right here, 4, 1, is a point on this line. It is not a point on this line over here, okay? Because that ordered pair is going to be the point that they share. So that's how we do that algebraically. But today we're really going to focus on solving systems by graphing. So the solutions to a linear equation are on its graph. So when I graph a linear equation, just one, all the solutions to a linear equation are just every single point on that line. But the solution to a system of linear equations is the point they share. They both have that point. Thus, it is the point of intersection. Let me rewrite that. It is the point of intersection. The point they share. So there are 3 different types of solutions. The first one is I can graph 2 lines and I can visually see the point they intersect. That is my solution. I have one solution. So if my lines are intersecting lines, then I will have one solution, and it's the ordered pair that they share, right? But what if I have, in the second example, what if I have parallel lines? Well, if the solution to a system is the point at which they intersect, how can I have a solution for parallel lines? I don't. They won't ever have the same point. So there's no solution when you have a set of parallel lines. Well, what if I have the same line? And you can kind of see there's the blue line and then the red line is graphed on top of it. It's the same line. We call that coinciding lines. So if you want to just write same line, there are infinitely many solutions. Now, one of the things I love about math is all the little symbols that we can use. If I have no solution, a set of parallel lines, and my answer is no solution, I could do that. It means the same thing. No solution, empty set, no solution. Infinitely many solutions. I could put a little infinity sign right here. That means infinitely many solutions. A lot of students really get these parallel lines have no solution, coinciding lines have infinitely many solutions. A lot of students get those mixed up. But the more you practice, the better you'll get. So let's look at these 4 examples. Solve each system of equations using the graphing method. State your solution as an ordered pair. Some answers may contain special solutions, which means no solution or infinitely many. So you have to be really good at graphing lines today because you're graphing a lot of lines. I like to graph in slope-intercept form, so if it's not in slope-intercept form, we're going to need to convert it. Thankfully, both of these on number 1 are already in slope-intercept form. So let's look at this first one, and I'm going to graph it in blue. Y equals 4x minus 3. What am I going to graph first? My y-intercept is negative 3. My slope, if you want to write 4 over 1, you can. And if you want to do this, 4 over 1, your y-intercept is negative 3, you can do that as well. So my slope is, I'm going to rise 4 and run 1. Run 1. And I like to put as many points on my coordinate plane as possible when I'm solving a system of equations by graphing, because my solution, if I have one, is probably one of those points if I have to do this by hand. Over 1. And then I'm going to draw my line as straight as I possibly can. If I had a pencil and paper, I will absolutely put a straight edge up to it and graph it that way because I like all of my lines to be perfectly straight. So now let's do the next one. My slope is negative 2. I'm going to write that negative 2 over 1 if you want. And my y-intercept is 3. So the first thing I'm going to do is graph my beginning point at 3. And my slope is negative, which means it's going to end up looking like that. If I don't have that type of slope, if I accidentally did it that way, then I graphed it the wrong way. Erase it and redo it. So negative 2 over 1. I can go down to, over 1. Look at that. Down to over 1. And you know what? I'm not even going to continue because I can obviously see that point of intersection is what? Right here. That is my point of intersection. The ordered pair is 1, 1. Let's move on to number 2. Number 2, I have two equations. Both are in standard form, so I need to convert them to slope-intercept form. So in this first equation, or right here, 4x minus 2y equals 8. I'm going to subtract 4x from both sides. So I end up getting this. And then I'm going to divide everything by -2. Now, you may have seen me in my previous videos. I write stuff like this. Everything gets divided by -2. The more that I do this, the less that I will write every single step down. So if you're struggling with this part of it, you need to go back to those lessons and make sure you can convert from standard to slope-intercept form. So when I divide everything by -2, I end up getting y equals positive 2x minus 4. And that's one line that I'm going to graph. Let's go ahead and graph it. First thing I'm going to do is graph my y-intercept at -4. And then my slope is positive 2. That's 2 over 1. So from that beginning point, that y-intercept, I'm going to go up 2 and over 1. And again, I like to put as many points on the graph as possible, because 19 times out of 20, nay, 99 times out of 100, your solution will be one of those points. Let's do the next one. 3x plus y equals 1. I need to solve for y, so what am I going to do? Subtract 3x. Y equals -3x plus 1. And there's the next line that I'm going to graph. What do I graph first? That y-intercept of positive 1, and my slope is -3. So I can go down 3 over 1 this way, and what do you know? I've already got my point of intersection. I can always go up 3 and over 1 this way, but do I really need to? No, because I can already see that point of intersection. Whoa, terrible line, but that's what it looks like. And then right here is my point of intersection. What is that ordered pair? Right 1 down 2 is 1, -2. Let's go on to number 3. Number 3, awesome. That first equation is already in slope-intercept form. So I don't need to do anything to it. Let's just graph it. Remember, if I don't have anything in front of my variable, what can I put there? A 1. So what am I going to graph first? My y-intercept, which is -4. So I go down 4 from that origin where those two axes meet. And my slope is positive 1. So I'm going to go up 1 over 1, and it looks just like this. Right, and I can put as many points as I want, or you don't have to. And let's draw our line as best as we can. And then let's do our other equation. So x minus y equals 4. I'm going to put a 1 in front of that y, and a 1 in front of that x. So the first thing I'm going to do is move the x term over. So -1y equals -1x plus 4. And now I'm going to divide everything by -1. So y equals positive 1x minus 4. And you can then rewrite it as x minus 4. If you don't need to put the 1 in front of your variable, you don't have to. It does help a lot of students. Well, right here, what do you notice? It's the exact same line. It's this right here. So the solution to this system of inequalities would be what? If the solution is the point they share, well, they share all of their points. So I have infinitely many solutions. Infinitely many solutions. Let's move on to number 4. Okay, so my second equation is already in slope-intercept form. Let's convert this first equation to slope-intercept form. And what do I do first? I move my x term over, so minus 2x. I've got -5y equals -2x plus 15. And then now what do? I divide both terms by -5. So I end up getting positive 2/5 times x minus 3. And what do you notice? Well, let's see here. I've got 2/5 x plus 2 and 2/5 x minus 3. If it's not jumping out at you first, let's graph it. So I'm going to graph this first one up here in green, 2/5 x plus 2. So first I'm going to graph that y-intercept of 2. I'm going to go up 2 and then over 1, 2, 3, 4, 5, up 2 over 5. And I'm going to do the same thing this way. And then I'm going to graph my line. Now let's graph the second equation. 2/5 x minus 3. Okay, that means my, did I do that right? I did. Okay, so negative 3 is my y-intercept, and I'm going to go up 2 over 5, up 2 over 5, and then I can go down 2 over 5, down 2 over 5. And what do you notice? These are parallel lines. When you're given your equations, how could you see before you even graph these that they are parallel lines? They have the same slope, 2/5, 2/5, but they have different y-intercepts. If they had the same y-intercept, it'd be the same exact line. But now these are just parallel, which means they will never, ever, ever intersect. So my solution is no solution. And this concludes your notes over solving systems by graphing, using the graphing method. Be really, really good at solving for y and graphing lines. I hope it was helpful.